Good morning, good afternoon, and good evening. Thanks for watching this video. In this video, we will cover strategic budget selection in a competitive auto bidding world. The conference version of this paper has been accepted in the STOC 2024. I am Yiding Feng, and this is a joint work with my amazing collaborator, Brandon and Alex from Microsoft Research. The motivation of this project starts from the following observation. Nowadays, in many online platforms, the market participants started using algorithms to help them make their decision. For example, in the online retailing platform like Amazon or eBay, the third-party seller will using some algorithm to dynamically decide the price of their item. And in the digital advertising market like Google Ads, the advertiser can use the automated bidding algorithm, which helps them to decide their bid for each of the ad auction. And there are some other applications, including Airbnb and Expedia. And in all those applications, again, so the market participant, the user, are using learning algorithm to help them make their decision. And the important feature I would like to highlight here is that all those users are using learning algorithm in a competitive environment. Because of that, we can observe very interesting behavior like algorithmic collusion, flash crash, and so on. And in addition to this competition across different algorithms, we would like to highlight that there is also a meta competition between the human users who are using those learning algorithms to compete against each other. And in the informal research question we would like to ask in this project is how will users behave in this meta competition where they need to delegate their decision to the downstream learning algorithm? And what will be the impact on the market efficiency given this new paradigm where the human user will using learning algorithm to help them to do competition? And in this work, we will try to answer this question in the context of digital advertising. And let's try to use sponsored search auction as an example. So whenever we search some keywords on a search engine, it will create some opportunity for the search engine to display some ads. And how the ad will be allocated is as follows. Whenever a search query appears, the search engine will create an auction instance, and then it will reach out a pool of advertisers who are relevant to this search query. Each advertiser will then decide a bid for this auction. And based on the bid, the auction will decide who's the winner, meaning whose ads to be displayed, and how much they will be charged. And as you can imagine, so from the advertiser's perspective, this is a quite complicated task. And this is because all the search query will appear in an online fashion. And because of that, the auction instance also appears in the online fashion. And different auction correspond to different search query submitted by different users who may have different location preference. In other words, all the auction instance might be heterogeneous. Therefore, from advertiser's perspective, this is a high-dimensional real-time decision making, which is super complicated. And to help advertisers to make better bids. So recently, there's a new technology called automated bidding. So here you can see the news article introducing this automated bidding and Google's own description of this technology. So what's happening here is that you can imagine there will be a middle layer between advertiser and the auction. In particular, each advertiser will be equipped with his or her own auto bidder. And then advertiser just need to specify some very simple instruction, like the daily budget, the maximum bid to the auto bidder. Then the auto bidder will serve as a proxy for their advertiser and decide the bid for the downstream auction. And they will optimize their bid by following the instruction like the budget and the maximum bid imposed by the advertiser. So if you look at this three-layer structure, you should imagine that so there is an inner competition between the auto bidder who need to decide the bid for each of the auction. And there is also a meta competition across the advertiser whose action space is basically the instruction they need to impose to the auto bidder. And in this work, we would like to understand this meta competition and how what is its impact on the market efficiency. Now, let me give you a short summary of our paper and the results. In this work, we build a framework where advertisers can strategically choose how much budget their auto bidding algorithm has to work on at auction, as well as a maximum allowed bid. we will assume that the advertiser's payoff will be determined by the downstream auction equilibrium, which are induced by the auto bidders competition. And in this work, we will particularly focus on the first price auction, which are widely used in the digital advertising industry. In terms of the results, we are able to show that for any pure Nash equilibrium of this metagame across advertiser, the result market allocation is always a true approximation to the optimal lead welfare, and this is tight and optimal. And we can extend this result to be a full approximation to the max Nash or Bayesian Nash equilibrium. And we are also observing some other interesting observation, like if advertiser can only specify a maximum bid, but not the budget, then this approximation factor can be as worse as the number of advertisers, which is typically super large in this application. So here is a related literature of our work. So because nowadays automated bidding become a super prevalent implementation in the practice. Like for example, in some major advertising platform, more than 80% of the traffic now need to go through this auto bidding system. Because of that, this, as you can see here, so it motivates a ton of recent literature which study how to design the automated bidding algorithm and how to design the auction to fit the automated bidding algorithm better. And there are also some other study like incentive compatibility in the auto bidding, the metagame between the learning algorithm, but not necessarily in the auction setting. And I will not dive into the detail of this slide. You can feel free to stop this video and take a look. Cool. So in the next few slides, I will introducing our model, which recaptures this meta competition between the advertiser and the downstream inner competition of the auto bidder. So imagine that we have T round. In each round, one ad impression will be auctioned by some auction format. Let's say we have an advertiser, and each advertiser will be equipped with its own auto bidder. The advertiser will need to specify a budget constraint and the value, or can also interpret it as a maximum bid to the auto bidder. Then in each round, each impression will be associated with a click-through rate, phi-it, which you could interpret as the probability that the user will make a click if the ad of advertiser I's ad has been displayed. And this could be heterogeneous and over advertiser as well as over impression. And facing this click-through rate, the auto bidder need to decide a bid, BIT, which is at most phi-it times VI. In other words, you could interpret this value VI as a valuation for the click. And in this work, we will assume that the auction will resolve the allocation. Basically, so you could interpret it as a probability of display each advertiser's impression ad to each impression and the corresponding payment. In the next few slides, we will dive into the detail of each layer of this three-layer system. First, let's think about advertiser. So in our model, we assume that each advertiser will have a separable preference. Specifically, given the allocation and the total payment, we will assume that the utility of this advertiser will contain two components. The first component is her valuation for the total number of clicks it received. So here we will assume that this valuation function will be weakly concave. It could capture the standard linear utility. It could also capture the decreasing marginal value. And the second component is related to the payment. Specifically, we will assume that the advertiser will have a DC utility for spending money, and this DC utility will be weakly convex. And this will capture the classic preference model as linear preference, budgeted preference, or the value maximizing preference, which has been studied extensively in this automated bidding literature. Now let's think about the auction and auto bidder. So we will in this work, we will assume that each impression will be sold by the first price auction. Specifically, given the bid submit to this auction, only the auto bidder with the highest bid can win the allocation. And if there are multiple bids which are both highest, we can consider arbitrary tiebreaking rule, which will not hurt our results. And the payment will be the first price payment, meaning that the payment will equals to their bid times the allocation. And we will assume that each auto bidder will decide the bid for each of those impression first auction by the first price auction in order to maximizing the total value. In particular, the objective function is the total number of clicks they will receive. And they will need to satisfy two constraints. The first constraint is the budget constraint, that the total payment cannot exceed the budget specified by the advertiser. And the second constraint is the maximum bid constraint, meaning that for each bid, it cannot exceed the value or maximum bid for a click times the phi t, which is the click-through rate. And this maximum bid constraint in our setting is also equivalent to the return of the spend, ROS constraint in this literature. And let me remind you that here, both budget and maximum bid are specified by the advertiser. Now we could ask, so if the auto bidder will try to maximize the value, how should it do? How should it decide the bid? Well, in this industry, so a very practical implementation is called the multiplicative budget pacing. Specifically, for each auto bidder, it will maintain a pacing scalar, alpha IT, which is between 0 and 1. And then in each round T, auto bidder will just bid alpha IT times phi IT times BI. In other words, it will scale down the maximum bid for this impression by alpha IT. And then based on the whole realized history, like the remaining budget, the auto bidder will select the alpha IT plus 1 for the next impression. And in reality, this pacing scalar might be updated by, for example, stochastic gradient descent. And the rationale behind this budget pacing that follow. So suppose that the single round auction implement for each impression is truthful. Then we know that there exists alpha I star, such as if we using this uniform pacing multiplier for all impression, it will be optimal in hindsight, given an arbitrary fixed profile of the bid of other opponent. In other words, this alpha I star is the exposed dominant strategy for this auto bidder. And as we mentioned in the previous slide, in this talk, we will assume that the auto bidder is trying to do value maximization, meaning that it wants to maximize the total number of clicks subject to the budget constraint and the maximum bid constraint. In such a scenario, it is known that the single round first price auction is actually truthful. And this is basically the intuition that why we want to do this budget pacing for the auto bidder. And in particular, so suppose we are given this budget constraint and maximum bid constraint, people have defined this notion called the first price pacing equilibrium, which is basically a profile of the pacing multiplier for each of the auto bidder, such as each auto bidder will just do the uniform pacing for the bid over all impression. And we will assuming that the induced allocation and payment will satisfy the following 6 conditions. The first 3 conditions is basically that the auction are sold by the first price format. So in particular, we can assume that each impression, each item will be associated with a per unit price, which equals to the highest bid. And only the auto bidder with the highest bid has a chance to win this item. And the tie breaking can be arbitrary. And the payment will be the first price payment. And the 4th and 5th constraint correspond to the constraint that auto bidder to satisfy, the maximum bid constraint and the budget constraint. And in particular, as you observe that the maximum bid constraint is satisfied because we assume that alpha I is smaller than 1, and the bid is equals to alpha I times the maximum bid. And the last constraint is called no unnecessary pacing, basically means that from auto bidder's perspective, either the budget constraint is binding or the maximum bid constraint is binding. And in the literature, in this beautiful paper, people have shown that this first price pacing equilibrium always exists. And moreover, its pacing multiplier, alpha I, and the per unit price, PT, for all impression, they are actually unique. And here, this pacing multiplier essentially is the optimal pacing multiplier we discussed in the previous slides. And have been equipped with this first price pacing equilibrium as a concept which we need to use to model the competition of the auto bidder. Then we're able to finish our whole model. Specifically, in this meta game of strategic budget selection, the advertiser needs to strategically decide the budget and the maximum bid, which will be reported to the auto bidder. And then, given the reported budget and maximum bid as an instruction, we will assume that the auto bidder will play this pacing game, and the allocation and payment will be induced by the first pricing pacing equilibrium. So if you pause here a little bit and think about this three-layer structure, so you can also interpret our model as the advertiser are facing a non-truthful mechanism, which is a combination of the auto bidder and the downstream simultaneous first price auction. And in this non-truthful mechanism, the message space of each advertiser are restricted. In particular, even though they could have a very complicated preference, which have concave valuation for a click, convex disutility for spending money, here we will only consider a very restrictive, very small message space, which is just a two single number, the budget and maximum bid. And in the next few slides, we would like to analyze the equilibrium induced by this game, as well as the market efficiency. So for the first set of the results, we are able to show that if we are consider homogeneous impression, homogeneous item, meaning that the click-through rate over all items are identical, but this could be different for different advertisers. In such a scenario, we're able to show that pure Nash equilibrium always exists, but this may not be unique. However, if we consider heterogeneous item, the pure Nash equilibrium may not be unique and may not be exist. And however, if we go to mixed Nash equilibrium or Bayesian Nash equilibrium, such a solution concept will always exist. And here I would like to make this comparison between the equilibrium in our meta game compared to the first price pacing equilibrium in the downstream competition across the auto bidder. Recall that for the first price pacing equilibrium, in the literature, people have shown that it always exists and unique. However, here we're able to show that if we consider this upper layer, the outer competition across advertiser, then we're able to show that pure Nash equilibrium is neither exist, it may not exist. If it exists, it may not be unique. And this shows a difference between the competition of the downstream auto bidder and the competition of the advertiser. And therefore, the knowledge we have established for the competition or the dynamic of auto bidder may not be extended to our advertisers' competition. Now, I would like to talk about, so what will be the impact of this competition across advertiser on the market efficiency? And to do so, so in this work, we will try to measure the market efficiency using this notion of liquid wafer. Specifically, given an allocation X across all impression, all items to the advertiser, the liquid wafer will be defined as a summation of the willingness to pay from each of the advertiser, given his or her own allocation. And this liquid wafer is equivalent to the social wafer if the advertiser has a linear preference. It is also known as a compensation variation in economics. So here is a simple geographical illustration of the liquid wafer. Suppose this is the total number of clicks the advertiser I received, and then so we can pin down its valuation, and then pin down the corresponding willingness to pay. And the liquid wafer is a summation of the willingness to pay across all advertisers. So as a main result of this work, we are able to show that in any pure Nash equilibrium of our meta game, the induced allocation will always achieve a liquid wafer, which is at least a 2 approximation to the optimal liquid wafer among all possible allocation. And this approximation factor of 2 is tight. And this result is also can be interpreted as a price of energy results. And the caveat here is that, as we mentioned before, so for pure Nash equilibrium, it may not exist in our meta game. Then we are able to consider the mixed Nash equilibrium. For the mixed Nash equilibrium, we are able to show the similar results, but the approximation ratio will become 4. And similar results can become extended to the Bayesian setting, where advertisers have private preference drawn from some prior distribution. And the takeaway message of this type of results is that simple instructions for the auto bidder are sufficient to achieve good market outcome, even if advertisers actually have much more complicated preference. In other words, even if the advertiser has a misaligned incentive with the auto bidder, only allow such a simple instruction like budget and maximum bid is already enough for the whole platform to achieve good market efficiency. In the next few slides, let me give you a taste about how can we prove those results. In particular, here, let me try to show you the key ingredient to show the two approximation for the pure Nash equilibrium. To show this result, a key technical lemma we are able to show is the following condition for the allocation and price in any pure Nash equilibrium. So here, capital H corresponds to all the items whose allocation is positive for this advertiser. And the intuition behind this inequality is as follows. Imagine that we are selling a single good with a fixed price P to a buyer without budget constraint. Then we can ask, so how much fraction will this buyer would willing to purchase? Well, to answer this question, we can consider its first order condition. And this is essentially equivalent to our equation. It is very similar to the equation we have in the lemma, but with two differences. First, we will have this price distortion term, because in our setting, the deviation of the budget or maximum bid will have the impact on the price induced by the competition across the auto bidder. Moreover, the equality becomes inequality because in our setting, advertiser has a hard budget constraint. And given this key lemma, we're able to show our two approximation for pure Nash. In particular, we want to bound these differences between the willingness to pay for a fixed advertiser given the optimal allocation and given the allocation induced in the equilibrium. Specifically, we want to bound that the difference between the willingness to pay is that most PI, PJ, which is the per unit price, times the YJ. And why this is enough? Because the difference is the total difference in the liquid wafer it can be written as a difference of this PI PJ times YJ over OI. And then we can replace YJ with XIJ. Then this will be the revenue of the pure Nash equilibrium. And we know that revenue is upper bounded by liquid wafer. Therefore, we show what we want. And to show this, to bound this gap, we can basically use this geographical interpretation, which we can first use a concavity on the valuation function and convexity of this cost function for spending money. And we will replace the willingness to pay by the total actual payment. And we will invoke our key lemma in showing the previous slide. And after rearranging the term by some algebra, we show our results. And finally, I would like to talk about some other interesting results in our paper. Consider two variants of our meta game, where in variant 1, the advertiser can only specify a budget constraint, but cannot specify the maximum bid to the auto bidder. And in variant 2, we consider vice versa, where advertiser can only specify the maximum bid. So when the advertiser can only report budget constraint, we can show that all our market efficiency guarantee still preserved. However, if the advertiser can only specify a maximum bid constraint, we can construct an instance such as there exists a Bayesian Nash equilibrium, which is an approximation to the optimal equilibrium. And this highlights that in the auto bidding system, allowing advertiser to specify a budget constraint is important. So to have a quick summary, so in this work, we are trying to understand this in this new paradigm in the digital advertising, where advertiser or human user will try to use some learning algorithm, automated bidding algorithm, to competing against each other. And we study this competition across advertiser. In our framework, we allow advertiser to have general preference, and we are assuming that the downstream allocation and payment will be induced by the first price pacing equilibrium. We're able to establish the efficiency at the equilibrium, which are approximately optimal in terms of liquid wafer. And we also observe this interesting message that budgets are necessary. Otherwise, poor approximation can be achieved in some instance. And that is all of my talk. Thank you for listening.